Hi, welcome to episode number 10 of the Cosmic Pie. So today I'm here with,
Robert Moore.
my name is Wayne Barkhouse. We are the regular hosts of this podcast. Once in a while we have to step aside, of course, depending on what's happening in our life.
Yep.
And we may or may not have people to fill in for us. Now, unfortunately, last week, which would be April the 4th, the university was closed because of a blizzard warning at the time. Even, well, should we say it? We really didn't get the blizzard until
We didn't get the blizzard until
late
Tuesday
April?
night.
Yeah,
Tuesday
late.
night, Wednesday morning. Yeah.
Yeah, so we could have done it, right?
Right.
But, once the university closes, we don't like to enter the buildings because if something ever happened. I don't think we're insured for that, Robert.
I'm pretty confident we're not.
Yeah,
So, and I'll mention again that the reason I glance off this way like this is because Wayne and I are in the same room. Okay, we're just using two different cameras. So when I'm looking over, it's nothing going on other than he's talking in the same room. So it seems really weird not to be looking at somebody talking in the same room with you.
right. And this is a conversation type podcast.
Absolutely.
Exactly. And we do have a live chat that's running, so if you have any questions for us, feel free to enter those questions on the live chat and we'll answer them as soon as we see them. The other thing I want to mention too quickly is that, of course, anything that we say on this podcast is just, of course, due to Robert and I. It is nothing or not necessarily the opinion of anyone else in the University of North Dakota, nor our department, nor our college, etc., etc., etc. We always have to say that just in case somebody gets upset what we say.
Yeah. Get upset with us.
Yeah, it's not a reflection of our institution or our place of work. We'll put it that way.
Right.
Now, Robert, so last week, April 4th, we were under a blizzard warning at the time.
Right.
But now it is April the 11th as we're live on this podcast, and spring has sprung.
Spring has sprung. I mean, the great melting, or also known as mud season, has definitely begun.
That's right. So going forward, it doesn't look like we're going to get hammered with any more snowstorms. Knock on wood. Now listen, you'll hear it. But the flood season is beginning.
Yes.
And that can be nasty around these parts.
Right. And because it's pretty flat up here, so if the river starts flooding, it floods. It goes everywhere.
And of course, in the city of Grand Forks since 1997, when we had the last major flood in the city, this was long before I was here, they did build a flood protection system. Yep. And now we are safe, essentially, unless we get a really, really, really extraordinary flood season. And that is not what we see predicted to happen this year.
Right.
So we are fine with all of that, which is nice.
And all of this might lead you to say, why would I think about coming to North Dakota? But you should still consider us. So.
Well, life is interesting.
Absolutely.
Right? Imagine if we just had like summer and the temperature consistently got to like 75 Fahrenheit day after day after day after day. After a while, you not only would you take it for granted, but it would be boring when it comes to be no seasonal changes, no nothing, right?
And then all of a sudden we got 103 a couple of days.
Yeah, or minus 30.
Or minus 30, yeah.
So we do have an interesting geographically, climate-wise,
here,
where we
yeah.
live for the different weather and stuff like that. But there's been a lot going on.
Absolutely.
Besides the blizzard last week in space and astronomy, I guess one of the most exciting things that's coming up next week, hopefully, this is one of these knock-on-wood things also.
Yep.
Well, it's been delayed a little bit, like what happens when you're developing space technology. You can predict, we'll be ready to launch our new rocket 2 years from tomorrow, but when it actually happens, well, that's it, right? A lot of it depends on any technical issues you may come across and so on and so forth. And so, Robert, if you want to show the first slide, and we'll talk about our first sort of news item that took our interest.
So there's our first one, yeah.
Yeah, so for those of you who may not recognize what this is the Starship that's being, it's already been developed and built by SpaceX. So this is down off the coast of Texas, not too far away from the border with Mexico. And it's going to go into sort of one loop around the Earth. It's like
I think that's
orbital
right.
type of orbital type of mission.
It's like the old Mercury missions. They're showing proof of concept that it worked.
Yes, that's right. So it's going to do essentially one orbit of the Earth just to see if the thing works. Now, The interesting aspect about the Starship is that it's actually the tallest and most powerful rocket ever to be launched. Imagine that.
Is it?
Yeah.
I wasn't sure of that. Is
It's
it
a little
bigger
over,
than the Saturn V?
yeah, it's a little over 360 feet tall. And
Okay.
there's talk of adding an extra piece to this rocket eventually, so it'll be even taller than that. An additional several tens of feet be added to it. And it's the combined, I believe it's 30 new Raptor engines that fire simultaneously at
Holy
the same
cow.
time. And that will produce somewhere on the order of roughly 15.5 million pounds of thrust at takeoff, which is way greater than the Saturn V
Yeah.
and a lot larger than even the SLS that recently launched several months ago by NASA,
Right.
which is the new, improved, latest generation of the Saturn V, if you want to think about it that way. This is the flagship sort of rocket that Elon Musk and SpaceX are going to use to get cargo and people to the moon and beyond, which means to Mars, essentially, and probably anywhere else you'd like to take it in the solar system.
He's really stuck on that, getting to Mars, isn't he?
Well, it's an interesting. It's like, I think, I don't know if it's true or not, but the story goes that Elon was looking to where to invest money
Okay.
several years back, and he talked to a lot of his people that he knew, essentially. And some people suggested getting involved in electric power vehicles, solar panels, and eventually the idea of rocketry got to him. And I think he was intrigued by the idea, why is it taking so long to get to Mars when we've been on the moon in the early 70s was the last Apollo flight. We first landed with men on the moon in 69 with Apollo 11.
Right.
And so shouldn't we been on to Mars like at least by the 1980s? Okay, we didn't make it. What about the 1990s? Well, here it is, 2023, and we still haven't landed people on Mars. Do we have to wait another 100 years? Well, Elon's not going to live that long, obviously.
Right.
So he wants to see things happening in his lifetime.
Okay.
And so I think he got a little fed up with the progress that was being made, and he took it from the point of view of free enterprise to see if business, could push this technology forward a lot faster than government. And I think the idea from Elon Musk, and I don't know if I'm right or not, but it seems this is what he has been saying, is that, if you want to do things slow and steady like a tortoise, then do it the government way.
Right.
If you want to get there a lot faster, do it the business way, the free business enterprise
I
way.
don't exactly disagree with him on that. Government's got to worry about astronauts blowing up in the sky.
Well, there's definitely a safety factor, and a lot of all that stuff now is government regulated. In fact,
Right.
the launch of Starship, which is targeted, the last I heard, for next Thursday, so next week, that's still awaiting FAA approval from the federal government.
Oh, wow. Okay.
And so they need to investigate everything, and they've done this already, right? But they need to do the final sign off of all this stuff, and a lot of that is for safety reasons, right?
Right.
They want people sending up, things that are put together really fast on the cheap and end up killing people. That's
Right.
not going to be good for anybody,
Or
including.
hit something on the way up.
Well, and there's obviously
clear airspace and all that.
coordination and all of that,
Yeah.
but yeah, they want things as safe as possible,
Right.
right? And I think the private businesses realize that, because what better to kill your program than have a major catastrophe where people lost their lives,
Right.
and that would be a good way to shut things down pretty fast, never to return, right?
Indeed.
So the idea is the Starship then is to be the workhorse eventually of
like to look at
SpaceX's desire to go to the moon, manned it, and also onto Mars with human-rated sort of spacecraft.
Yeah.
So that's the long-term goals. And so Elon said, okay, if it's taking the government too long to get to Mars, would people let me give it a shot? Essentially, in my lifetime, hopefully we'll get there.
Yeah.
And then everything follows from there. The biggest sort of issue that's always been around, this has been like this since the time that the space program began, is the cost per pound to put payload in space, right? So, initially the cost has been huge, like $10,000 per pound. And I've heard arguments that really by the time the cost can get down to $100 per pound, that's when it makes worthwhile to put things in space, whether it's space probes going to different planets or objects, let's say, in orbit around the Earth. And of course, as things get cheaper, then it's much easier for people who don't have a lot of money, maybe like universities, even, hobby clubs, So in the past, we've had radio hobby clubs that put together a satellite and actually got it launched. I mean, that happened a long time ago.
And
that was like
we've
late.
got the CubeSat
Yes,
revolution now going on.
Right,
so.
and so the sort of the extension of that program. I think it was in the late 70s, early 80s that the ham radio operators put up a satellite with that type of equipment on board. And then when the space shuttle came along in around 81 or so, the first launch of Columbia, they got the idea of putting these little kits inside the cargo bay, little experiments. You remember that?
Yep.
It's almost like CubeSats, but not quite. Right?
Yeah, they were kits, though, they could be loaded up into the space station and things.
Right,
Yeah.
and I remember at the time different universities had competition, right? You could propose an idea to put in one of these little kits, and they had enough money, like $1 million or a couple $1 million to pay for that. But of course, as things get cheaper, all of a sudden it becomes really easy to put up a lot of satellites. And with that, of course, we have this problem that we've mentioned in the past about satellite debris.
Right.
And this type
Satellites getting in the way.
Right, and so this type of thing is a real problem now. There's an estimated 9,000 items in space, and this is work.
That's all?
Yeah, this is like major satellites and things that are defunct but are still up there orbiting.
Yeah.
You're not going to count the individual pieces, because anytime you see a rocket launch, even today, you'll see things come from the separation of their stages, including the last stage, and a lot of that stuff is going to be at least in a short-term orbit.
Right.
Now, the Earth is a natural sort of vacuum cleaner when it comes to orbital debris, in the sense that the stuff that's in low Earth orbit will naturally come down because there's no hard cutoff in our atmosphere.
Right.
Now, where do we define space? How high up in the sky do you go before we get technically to space as most people define it?
Forget the name of it, but it's 90 kilometers. Isn't it 90 kilometers up?
Very close, 100 kilometers, and that's the Kármán line.
Kármán line. That's it.
Right?
Yep.
But it's not like you go from an atmosphere to no atmosphere, to the vacuum of space, right? There's a general decrease in the density of the gas as you go up. But even if you're at heights of several hundred kilometers in space, there's still trace wisps amount of gas that's up there. And that causes a drag, essentially a frictional force, if you want to think of it that way, to satellites as they're moving in orbit around the Earth. And that causes them to lose energy, essentially, and eventually re-enter. That is, the orbit will decay after a period of time. Now, the higher up you are, the more time it takes to decay, to the point where you get up so high that essentially you won't come back at all.
Right.
Right? There's just nothing there, right?
I'm going to bring up the point that, we tend to think and talk about space being a vacuum. And it's like, even if you get out past the moon, there's still the solar wind that's there. But now we're talking about 3 protons per cubic meter. Okay? And for those who aren't familiar with metric units, a meter is about a yard. So in a box, 1 yard by 1 yard by 1 yard, there's 3 protons in there. And so what are you going to call that?
Rarefied.
Rarefied. That's a good word.
That's the technical term for that, right? The near vacuum, right?
So, some people like to think that, there's absolutely nothing in space. No, there's stuff in space. It's just, it gets thinner and thinner the further away from other stuff you get.
Now, do you know what affects how high up our atmosphere is? Let's say you measure our atmosphere and you could define it, instead of the Kármán line, 100 kilometers up, you're quote-unquote in space, you get your astronaut wings, all these kind of things. You may define it as the average density of the atmosphere drops to a certain level.
Right.
Okay, you could use that as sort of some kind of fiducial way of defining where the atmosphere ends, right?
Right.
And we know it gradually decreases, with height, the density would decrease. But do you know the distance from the ground to what that level would be, that it's not stationary? It's not a constant with time, right? So what affects
goes in and out.
So what affects that? What's one major effect on our atmosphere height?
Solar radiation is
Exactly, it's the sun.
Right.
So when the sun is more active, that actually drives energy into our atmosphere and causes our atmosphere to expand outwards.
Right.
And that causes an increased drag then for these low orbiting vehicles. In fact, you might remember, and I'm old enough to remember, back in the mid to late 1970s, the space shuttle was due to be launched at roughly that time frame when they were initially planning, let's say coming out of the Apollo program in early 70s. They thought that the shuttle would launch somewhere around 77, 78, 79, and of course eventually that would change until 1981. And at that time in the 70s, Skylab was still in orbit around the Earth. So there was a suggestion by NASA that one of the early flights of the space shuttle would actually go to Skylab, attach a rocket booster to Skylab, and boost it into a higher orbit.
Okay.
And what actually happened was Skylab decayed in the mid-70s before the shuttle was launched, in part due to the fact that we went through a solar maximum at the time and caused the Earth's atmosphere to expand outwards to actually cause an increased drag on Skylab, which brought it in a lot sooner than what otherwise would have, than what was predicted.
Yep. And we still owe Australia money, I understand.
Right. So and that joke is the fact that pieces landed on Australia.
Yeah.
Now, most of it landed in the ocean, but some of it did land on the land in Australia itself. But our atmosphere it breathes. It's alive in that sense, if you want to think of it that way. So there are times when there's more drag. Let's say you have a satellite that's up a couple hundred kilometers above the surface of the Earth. It'll undergo changes in drag, not just because it's changing its height, but actually due to the expansion and contraction of our atmosphere due to the energy input, like I said, mainly from the sun.
From the sun.
Now, a lot of the low Earth orbiting satellites that are up there now, and there's more all the time, is the system that Elon Musk and SpaceX is putting up, the Starlink system.
Yes.
And there's a reason for that, and that reason is because if you had your satellites in geostationary orbit, it takes a little over a quarter of a second for light to get there and back. Now, if they're in low Earth orbit, it's less than that a bit. It's not a huge difference. But if you add in all the delay factors of your internet line links, or signals, I should say, going through networks, going through routers, going through servers, that adds up after a while. So there's like this latency effect where if you push your button on your keyboard, you want to see that went there instantly or near instantly as far as you can tell.
Right.
But if there's a delay, that some people don't like that. And so to get around it, they said, okay, let's put all our satellites in low Earth orbit. So the signal getting to there and back down to the ground station is a little bit less. It's not significant, but it turns out that latency is short enough that they don't think it really bothers people. And that's the main reason for putting it up. But because you're on low Earth orbit, you're not in a geostationary orbit, these satellites are moving with respect to the surface of the Earth constantly.
And they're already coming down.
Yeah. And so what you need is to have lots of them, so that at any given moment at some location, let's say here in Grand Forks, we want several satellites above us so we can receive our satellite internet signal. Right. It's almost like having enough satellites. I think 3 is the minimum for triangulation when you're using the GPS system.
Right.
That sort of thing. And so since these things are moving all the time, you need literally you've got to put up hundreds, thousands of these satellites. But what's already happening, I noticed, and this was on the news also last week, is a lot of these satellites are starting to re-enter now because they're in such a low Earth orbit. And the sun is ramping up.
It's going towards maximum.
Yeah, in terms of its activity. So there should be more frequent, aurora borealis, both the northern and southern lights. We'll hear more reports in the news about that, or you'll see them yourself, and so on as we approach solar maximum.
Right.
And so that's some of the things we can listen to is any type of some more of the stuff coming down in the next few years. So
and you saying listening to reminded me, we might want to do a show about the auroras, because listening made me remember that a lot of people used to listen to the auroras by clipping on the telephone, the old crank telephones, onto barbed wire fences.
Oh, wow. Okay,
because
neat.
The fence would act as a big antenna for the radio emissions from the auroras.
Right. Well, that's kind of interesting.
Yeah.
That's cool. Now, there were reports that that you could hear the crackling sounds from aurora, but I don't think that's ever been, I think that has been confirmed. Don't hold me to that, but there's a lot of gray area there.
A lot of gray.
Yeah, but I think it's highly unusual that you'd get an audio type of signal transmitted through lower atmosphere due to these effects that's occurring. But, we're still studying the aurora. Right? We don't know everything about the aurora. That's an ongoing sort of stuff. There was a group out of Sweden that launched a rocket back in late March. I think it was March the 23rd when we had our last big aurora event. It was the biggest one in 6 years.
Right.
And this group in Sweden launched a rocket to make their own artificial aurora. And they were studying that at the same time that the natural aurora was going on, to try to put all those things together to get a better understanding of the interaction of electric and magnetic fields with the atmospheric particles and the stream of particles coming from the sun, which we call the solar wind, and how all that plays together. It can be a very complicated type of system, right? And even though we've been studying that system, the auroras for tens and tens of years now, for decades, we still don't have it all figured out. There's still lots of surprises.
There's still lots of stuff to discover. So
In fact, we're doing a lot of aurora type of work here at the University of North Dakota in our department, which is interesting. I'm part of doing that type of research, and I think in a future podcast we'll bring in one or more people that are that would talk a lot about it and that sort of thing. And so we'll say more about it later on when we get to that point. So that's something we're working on in the background.
Cool.
Now, Robert, did you have something you would like to bring up, one of yours news items, or do you want me to continue on with my list?
I was going to let you continue on with your items because you brought more to the table. So.
Okay, so there was another interesting news release that was done just a couple days ago. This is about the Orion Nebula. So here's an image of the Orion Nebula taken with the Hubble Space Telescope. And if you look very carefully in the image itself, you see these sort of bubble-like shapes or structures that you see there. There's the shock waves, actually. Right. And then if you see on the right side of the shock wave, the one that's sort of in the upper middle of the diagram of the image here, you'll see what's actually a star, a newly formed star. And if you look carefully, you'll see jets, bipolar jets, one jet going upwards and the other going downwards, right?
Right.
And this is due to the star being essentially in the last stage. It just, arrived on the main sequence. So it's a newly formed star with lots of debris still around it. And these jets then propagate outwards on 90 degrees or at right angles to the plane of the disk that makes up that debris field.
Right.
And these jets go above and below, if you like, in that sort of orientation. And you can see, the early form of these were known as big haro objects.
Big haros. Right.
So that's what you're kind of seeing here is the formation of these. Now, the Orion Nebula, which is somewhere in the order of a little over 1,000 light years away from us. So it's not in our backyard, but it's not on the other side of the observable universe. Right? It's in our own galaxy, fairly nearby, and it would arguably be the most extensive star formation region close to us.
Right.
And so if your goal in life is to study stars, like learn how they form in nitty-gritty detail, this is
no better place.
This is the place to look, right? In fact, you can see the Orion Nebula with the unaided eye.
Yes, you can.
In a dark location.
And you don't even have to be in that dark a location. I've seen it in suburban skies. So it looks like a fuzzy star.
Yeah, and it makes up, in fact, the sword of Orion the Hunter in the sky, which is a constellation you can see this time of the year. As soon as it gets dark, if you look towards the southwest now it's heading, you'll be able to see the constellation Orion. And so there's a nice, beautiful star formation region in Orion Nebula. It's nothing new in terms of studying. We astronomers have studied the Orion Nebula for many, many years now. Like I mentioned, this is from HST, so you get a nice high-resolution image of part of the Orion Nebula. You can only see part at a time here. But to explain the presence of these new stars, it's through cloud-cloud collisions. Now, there's always been this talk of how do you form stars?
Right.
And you could think of several scenarios. You imagine you had a cloud of cold material, interstellar matter. Ultimately, what you want to happen, of course, is you want gravity to do its thing, cause this object to collapse in on itself to the point where eventually core temperatures can reach at least 10 million Kelvin.
Right.
And why that number? Because at that number, you can smash together hydrogen, essentially protons, with enough force, if you like, that they stick together and form helium.
It's a neat process because you've got to have them fast enough, in other words, hot enough, that they can overcome the electric repulsion of two protons. But you can't have them going so fast, being so hot, that they ricochet off of each other.
Yeah, so you need them to hit with enough energy, I guess you could say it, such that they would stick together through the strong nuclear force. It would be able to engage, if you like, and then hold those protons together. And that's essentially, if you think about it, what we mean by nuclear fusion, in this case, hydrogen into helium.
Right.
Now, the net result of those type of reactions is energy gets released, and that's the energy that powers stars, at least when they're on the main sequence like our own sun. That's what's going on inside of the core of our sun. And so once an object has reached this point where it's able to have sustained nuclear fusion of hydrogen and helium, then it becomes a genuine star, as we would call it. Before that, it's a pre-main sequence star, and before that, and we have a protostar. So we have different labels for these type of objects.
And
Right.
It's, to me, it's real neat again, because it's not again, we talk about it like it's the smooth process, but this pre-main sequence star is collapsing, but then it gets too hot and it pulses back out and stops fusion, and then it comes back in, and it's a slowly deadening, dampened oscillatory system.
Well, it was interesting because what I heard was, let's say back in the 60s when the personal computers were starting to be developed, so that, like university professors at some point were able to afford one or
Right.
use the computer that's in the university itself that everybody shared back in those days.
Right.
Those who are working on star formation had a heck of a job trying to model how stars formed. In fact, with all of the input of physics, known physics that you think would be required,
Like-
they could never form stars.
Right.
So the joke was, you can think of the astrophysicists, the theorists at the time would try this experiment, run the simulation in a computer, couldn't get a star ever to form after trying and trying and trying, and then they would write a paper, stars don't exist. Like that would be the,
I remember those.
it's that kind of
But it's about, like, at the same time, we couldn't model how bumblebees flew.
right.
So there were papers in the engineering side talking about how bumblebees can't fly.
Right. So
So,
that's
yeah.
the joke. Obviously, Mother Nature makes stars. Mother Nature allows bumblebees to fly from one location
Right.
to another. So we just haven't had to figure it out, the puzzle, right? We need to,
Right.
come up with the answers to explain what's going on. So really, by changing the initial conditions, changing the starting temperature, and so on, then eventually simulations were able to show that how stars could form. So that just furthered our understanding of what's going on. And back in that time period of many decades ago, our ideas of star formation from the point of view of direct observations were relatively crude,
Right.
right? And so with the development of instrumentation, of specialized telescopes, of things that could better uncover what's actually happening when stars are forming, looking in stellar nurseries like the Orion Nebula,
Right.
then you can get a better understanding of what is the crucial input physics that you need.
I mean, I was still in college at this point, but I remember when the first pictures of the Orion Nebula came out from HST, and you could see these circumstellar disks with the protostar embedded in them, and you could see these new stars blowing out gas and dust like that bow shock wave you saw on the image. I was sitting there going, "Oh my God, this is wonderful," So yes, better instrumentation has led to improvements in what we understand and how we understand it.
Yeah,
So,
do you remember what those objects in Orion Nebula were called?
proplyds?
Yeah, exactly.
Yep.
And those along with like cocoons. The stars were forming inside these cocoons. One of the things you could look at is how does the brightness of those objects change with time? Look for variability and
Right.
those sort of things. So there are a lot of interesting science, of course, that you can do.
Absolutely wonderful stuff. So yeah,
Right. So when you try to figure out where stars come from, right? So we need for gravity to eventually do its thing and
Right.
collapse material to form stars. But the questions that we always had is how does that process get triggered?
right,
Now you could think of things that would trigger a process like that. For example, an exploding massive star, right? What we call a supernova, that would blow up, and the shock wave that gets generated in this type of explosion propagates outwards, runs into, let's say, interstellar matter that's nearby, and that shock wave can initiate a collapse of material where the point where gravity does its thing, the runaway collapse effect, right?
again, you can see this effect modeled by if you've got a puff of smoke, and you blow against it. You can see areas where your breath of air shocking into that cloud of smoke will make areas of higher density, thicker smoke. And the same type of thing is thought to happen.
Now that process is great, but of course, if you want to understand what about the first generation of stars, there are no
that's a bigger-
supernovae
right.
to create a shock wave, right?
Right,
So then we could think of other things. Well, when you look at very massive stars, in astronomy we call those spectral classes O and B type stars. These are stars that have surface temperatures on the order of 35,000 to about 50,000 Kelvin. And in comparison, our own sun is just a little bit less than 5,800 Kelvin. So these are many times hotter than our own sun on their surface. These are massive stars, up where the highest mass star nobody really knows. We think it may be on the order of 100 solar masses, and it depends on what is the composition of the material that it came from. And so there are, that's a whole podcast and trying to understand.
Oh yeah, probably
trying to understand that. But these high mass stars, and they generate a tremendous amount of light, of radiation. That is, they have very high what we call luminosities. You could think of them as the wattage of a light bulb.
Right.
So imagine taking a 60-watt light bulb and replacing it with a 20,000-watt light bulb. The difference in brightness when those two lamps are at the same distance away from you. So there's no distance effect that you're looking at or anything like that.
If you're 20 feet away, let's just say the 60-watt light bulb isn't going to warm you up any. But if you're 20 feet away from that 20,000-watt light bulb, you're going to get cooked.
Well, especially the old incandescent light bulbs would throw out a lot of heat. The newer ones now, you can touch them when they're on; they don't burn you because most of that energy comes out in the form of light rather than coming out in the infrared, right, as heat. Yep. But that'd be a good way to get maybe a suntan in the wintertime around here. Yeah, one of those here. But yes, so you have these really massive stars pumping out a tremendous amount of energy, including radiation is what we mean here. And that radiation has in physics what we call momentum. And so it has the ability to push on things.
Right.
Okay. And so that can cause interstellar matter that happens to be nearby. Maybe it's the leftover debris from the formation of these massive stars. That can cause that material to collapse in on itself once again through a pushing process to allow gravity to do its thing and collapse the object, ultimately would turn into a star. But once again, we have the same issue. You need to have these massive stars nearby. You need to form those massive stars in the first place to create star formation to allow.
Right.
So there must be a third process at least that doesn't rely on the fact that a star must already be around or have existed, like a supernovae or like these really massive OMB type stars. So that third process is what the slide is illustrating if we want to go back to the Orion Nebula.
Okay.
And in the Orion Nebula, what we're seeing evidence for here is collisions between clouds.
Oh,
so
right.
think of the Orion Nebula as a giant molecular cloud, if you want to write it that way. And within this giant molecular cloud, the material is not smoothly distributed everywhere. It comes in clumpy fashion. Like you can think of it as cloudlets. And if you actually look at this image, you can see there's structure in the cloud. It doesn't look plain, like looking up in the blue sky or anything like that.
Right.
It doesn't look smooth and, I would say, isotropic and homogeneous.
Right. Which those words, by the way, just mean it's smooth, that it's the same everywhere.
Right. So isotropic means that regardless of which direction you look in, everything will look the same.
Right.
Homogeneous means if you physically moved your location to somewhere else and then looked around, everything looks the same. So it doesn't matter where you are, everything looks the same, and it doesn't matter where you look, everything looks the same.
Right.
That's what we mean by those terms in physics, right? That's what
Right.
we're referring to. But in the Orion Nebula, we don't see that. You can see structure, you can see things. So there are different cloudlets, if you're like, and they're all moving around, right? It's not like it's motionless, even though in this image is sort of a snapshot in time. If you could watch it, later on, and then later on, and then later on, at a later and later time, you could put that all together as a movie. Now, you might have to wait a long time to see motion. But
a few tens of thousands of years.
But you'd see motion nevertheless, as this whole complex is orbiting around the Milky Way galaxy, right?
Right.
So within the stellar nursery that we see here, then clouds can run into each other if they happen to be on trajectories or paths that take them on a collision course. Right. And in that colliding of clouds, that can change. That can trigger star formation.
That can produce a pressure wave that trigger it.
And that does not rely on the presence of a first generation of stars. In fact, you can use that then to describe where did the first generation of stars come from. It might have come from the collision of clouds that would have triggered it. Of course, you always have just your normal gravitational collapse of a cloud of material, but we're talking about something that's in motion. Maybe there's angular momentum associated with it, that is spinning type of motion. That makes it more difficult for gravity to pull things together where you have temperatures hot enough that allow you to exceed 10 million Kelvin in the core and initiate this nuclear fusion business. You see? So all of that are important considerations. So it's a really complex, really dynamical type of environment that we find these stellar nurseries, right, where the star formation process occurs.
it's great. Sorry, I get excited about star formation because that's kind of my thing with planet formation.
Right. So
They go hand in hand.
So we have star formation, and what's on the opposite end of that spectrum? No pun intended.
Star death.
Star death. So let's bring up the next one. This was something else that was in the news the last couple of days. This is a new image put together by the James Webb Space Telescope, looking at the leftover debris from a star that exploded approximately, it would be back like over 300 years ago.
Right.
Okay, back in the late 1600s.
This is one we have historical records about because people
No,
did write about it.
No,
they did
no.
write
I
about
think you're
this one.
talking about Tycho Brahe supernova.
I thought this was the one that the Chinese wrote about.
No, that was actually
Okay.
the Crab Nebula,
Okay.
right? That was like roughly 1,000 years ago.
Okay.
Right, 1054 AD, I believe that was.
All right.
Right.
So I'm getting my supernova
Yeah.
mixed up.
This
Okay.
is the one. Now, by the way, this is the result of the end state of a massive star that blows up.
Much larger than the sun.
And we had talked about this in a previous podcast, but just to kind of summarize really briefly, what happens to the really massive stars? And what do we mean by massive star? Anything that has a mass greater than about 8 times the mass of our own sun
Right.
when it's a main sequence star. Now, our own sun, if you like numbers, it has a mass of about 2 times 10 to the 30 kilograms.
Okay.
Now, I wish I had 2 times 10 to the 30 pennies in my bank account.
Oh, Lord, yes. Of
You
course,
know?
that would be more mass than the Earth. So,
Well, I just want the number, the dollar value of my bank
Oh,
account,
okay.
right?
okay.
I
So
could
the
pay off the
electronic
debt of every.
digits.
Yeah, electronic money.
Yeah.
I don't want to carry that amount of pennies around. But so these massive stars, what they do is they end up going through different stages of nuclear fusion. For example, we already talked about the fact the first stage is the conversion of hydrogen and helium. Then it's helium into carbon and oxygen, and then carbon gets to convert into heavier elements as it goes through, through its life cycle. And the end state of all this is iron. So you develop this iron core at the center of these massive stars. Now, iron, if you fuse it into something heavier, that requires energy rather than to give off energy from that reaction.
Instead of releasing heat to put an outward pressure, it takes in heat. It cools the star.
So if you're a fan of chemistry, we would call that endothermic reaction
Right.
rather than an exothermic reaction. So endo meaning into, exo meaning being
Out.
released, being
Right.
coming out. And so because of that, this is an end state then of the normal fusion process that occur inside of the cores of these massive stars. So what happens literally is that core of iron collapses in on itself in a very, very brief period of time. So fast, in fact, we call that an implosion, the opposite of an explosion. And during that implosion sort of time frame, what happens is that the temperature of these cores go to essentially billions of Kelvin, and that produces a tremendous amount of very short wavelength gamma rays because it's just such a high temperature. Those gamma rays have so much energy that they smash apart the iron atoms in the core. And so you have these individual protons, neutrons, and electrons essentially running around. And what happens is because of the extreme pressure of this imploding core is the protons join up with the electrons to form neutrons.
Yep.
Okay? And so what you end up with, you have neutrons that are already part of the normal iron atom are being joined by these newly created neutrons. And so you're building up the neutron abundance in the core of these massive stars. Those neutrons are jammed side by side, and then they resist further collapse. There's this thing that we call neutron pressure, if you want to go technical,
Neutron
degeneracy pressure. The way that I like to think about it is imagine putting marbles in a glass vase. Okay?
Mm-hmm.
So you have an empty vase and you pour in marbles, and the question somebody asks you is, how many marbles can you put in this glass vase? Well, I don't know. Let me see, right? So you have marbles. Let's say they're all identical. You fill up the glass vase, and as soon as you add one more marble to it, it just goes over the side. It never adds to the number of marbles that's in your vase. It's full for all
Right.
intents and purposes. Now, you could change things by taking that last marble and sitting it at the top of the pile, and at the same time push down with the palm of your hand, trying to force that last marble into the mixture. And if you're strong enough, or if the glass vase is also weak enough, it may break the vase, cause it to crack, right? You're exceeding
Right.
the volume that it can handle of these marbles. That's something what happens here. The neutrons get jammed side by side. There's literally no space between neutrons neutrons don't like to be on top of each other or inside each other. It's not a way you kind of think about it classically. And so they put out their elbows and say, that's it, I'm not getting any closer to any other neutron.
Yep.
So that creates this overall pressure, this neutron pressure. Well, the material that's on the outside of this neutron core, then it doesn't know what's happening inside the core. So it's raining down on top. And it would be like you, for example, let's say you ran into a brick, and don't do this, this is a thought experiment. Let's say you ran into a brick wall at 80 miles an hour, right? You could run very fast, right? Of course, you can't do that, but anyways. Go with me on this thought experiment. You run into a brick wall, what's going to happen? Well, either the brick wall will collapse, and if it is, and you're inside of a building, get out of that building right away because it's structurally unstable.
It's now.
Or what likely will happen if you run into a brick wall, you're going to bounce backwards. Right. And so what's happening is that material falls towards the center where this neutron core is, and that core is extremely stiff, essentially nuclear density.
Right.
And that material then rebounds back outwards to create this giant shock wave, essentially an explosion, that blows all that material outside of this neutron core outwards. And that's what you're looking at here in this image, is if you weighed it then over 300 years, what do you see? And this is known as a supernova remnant. Okay, this is the leftover debris from the explosion of a massive star.
So what lights it up? What makes it glow like this?
Right, and so number one, you have energy that's coming from the center core. Now that core itself is interesting. If we follow the logic here, is sometimes that core will maintain its structure, and that turns into something that we call a neutron star, right? If it has a lot of mass, more than about 3 times the mass of our sun, it will, in that process, will actually collapse in on itself to form something that we all love to talk about in astronomy, known as a black hole.
Yep.
Okay, that's how you form one of these from the end state of the supermassive star going supernova. Now, in this process of exploding, let's say you only form the neutron star, you're going to get a lot of energy that gets released in the explosion. And that energy comes from not only the light that's emitted, but also particles that get emitted, and they'll slam into slower moving particles. Essentially, a shock wave gets created.
Right.
And in that shock waves, these different material gets energized. If you know a little bit about atomic physics, you can think of it as electrons get boosted to higher energy levels, or even they get ionized, the material, so electrons get stripped away from ordinary atoms, for example. When those electrons recombine with the protons, or as they descend down the energy levels, they emit light. And this part of the light process that's being emitted here.
There we go. Yep.
Okay, so that's why we can see these supernova remnants. Now, to give you a sense of scale, the supernova remnant that we're looking at here, known as Cas A, and that comes from the fact that it's located in the constellation
Cassiopeia,
and that's the W or the M, depending on which way you tilt your head, that you can see in the northern sky. So it's one of these constellations that you can see all the time this far north. It's called circumpolar.
Right.
Right. And so as the Earth rotates, this constellation is close enough then to that rotation point, which is demarked nowadays by Polaris, or the North Star as we call it, that since it stays close to that point, it's always above our horizon locally.
Right.
Okay. So anytime it's dark, you can see Cassiopeia.
And having been from a location that's much further south, I will also note that it's still circumpolar for a good portion of the United States.
Right.
So.
And once you go below the equator, of course, then you get to the point where you can only see it occasionally, and if you go far enough below, you won't see it at all. Right. Just like we don't see Polaris or the North Star if you're in the southern hemisphere, right? It's below the horizon at that point. Now, so for a sense of scale, this supernova remnant is on the order of 10 light years in diameter. Amazing when you think about it. 10 light years, okay, in diameter.
And it got that way in 300 years.
Yeah, exactly.
The outer edge of that thing is moving pretty fast.
Now, it's interesting to know where was the star? In other words, where is the supernova remnant? How far is it from the Earth? It's about 11,000 light years away, it's estimated.
Okay.
So so the light that we see today coming from the supernova remnant left that remnant 11,000 years ago. Okay?
Mm-hmm.
That's even before I was born. You realize that, Robert?
I don't know.
Now, Robert, you did mention that maybe this was actually seen and documented in the past. Actually, it wasn't. This is one of these supernova that went off that should have been visible from the Earth, one would think, given its location. But notice it's not in our backyard. It's 11,000 light years away.
Right.
Now, it was never reported that there was an appearance of this new star in the daytime sky like some of these past supernovae have been reported. But there is a report, if you like, or at least some indication that the first astronomer royal in England, who was at the Royal Observatory in Greenwich, right, where we have our Greenwich Mean Time is, it's quite a 0 degrees longitude line, that the head guy, if you like, of that observatory back in August the 16th of 1680 may have recorded the appearance of a new star in the constellation Cassiopeia and never realized it was the supernova.
Okay.
So it was, serendipitously recorded, and that would have been done by John Flamsteed, if you recall the name.
Oh, Flamsteed, yeah.
So he did a lot of cartography, stellar cartography, that is writing the location of stars and and making diagrams of the constellations. So
one of the major catalogs of objects and where they are is the Flamsteed catalog.
So, so it looks like he recorded it, right? So that would have been just by random chance, of course.
Cool.
You see, but no one picked up on the fact. And you might ask, why is that? Well, 11,000 light years, there can be a lot of dust between us and the object, the star that went supernova. That would cause the light to be dimmer, diminished. And so it may have been, to the point where it really wasn't that bright and no one really recognized it as the appearance of some new star all of a sudden in the sky, whether it was the nighttime or the daytime. So this is one of these supernovae that we missed. In fact, the last supernova that was observed in our own galaxy was about 400 years ago, and that's in the time of Kepler, right? No,
that wasn't the Crab either.
Yeah, that was roughly 1,000 years ago.
That's right.
Right, that was the one in the
I'll
constellation Taurus.
Yes.
Yeah, so that was in 1054 A.D. Right. So the last was in the early 1600s by Kepler, just before Galileo turned his telescope to the sky. Right?
Okay.
Kepler, so it was naked eye observation, as we say, or the observations with the unaided eye. And there hasn't been a supernova that's been observable in our own galaxy since. In other words, since we've used telescopes and all this advancement in technology, we haven't seen one of these exploding stars in our galaxy. We've seen them in other galaxies.
The importance of that is it's close enough for us to actually measure and watch and see how it progresses. So.
Right. Now, the closest, I guess, we've come is the one that went off in 1987. This was in the Large Magellanic Cloud.
Right.
So this was observable from the southern hemisphere. You couldn't see it from Grand Forks. But that was the closest one in recent times, would have been that one. And so we're dying. That is, we're waiting for a star to explode.
Hey, come on, Beetlejuice.
That we can study in detail with all the telescopes that we have, both on the Earth and in space.
Right.
In fact, it's interesting to note that when the supernova went off in 1987 in the Large Magellanic Cloud, which is a low-mass galaxy or satellite galaxy in orbit around our own Milky Way, the Hubble Space Telescope was not in space. It was due to have been launched in the summer of 1986. But unfortunately, in January of 1986, do you know what happened in space?
Just say January? No, I
1986.
can't think of...
It was the explosion of the Space Shuttle Challenger. And the Challenger was scheduled to launch the Hubble Space Telescope in the summer of '86. So when the supernova went off, as viewed from the Earth, of course, in February of 1987, Hubble would have been in space.
Right.
And would have been able to make detailed observations of the supernova and its aftermath.
Right.
But it didn't get launched until 1990. But of course, when it did get launched, we discovered the mirror had the right shape. It was really nice and smooth, but it was to the wrong shape. And so we actually had to give Hubble eyeglasses to fix its vision, if you like, so then things were in focus. So that takes a couple of years to develop that. So we would have missed it anyways, with the nice sharp focus that Hubble has today, unfortunately. But, so NASA turned to backup instruments that we had. What do you have in space then in 1987 that could make detailed observations of the aftermath of a supernova? The IUE, the International Ultraviolet Explorer Satellite. That was a satellite space telescope, a small one, that was mainly observing in the ultraviolet wavelengths. Well, ultraviolet means it's coming from hot stuff. Right?
Well, that's what you want to study.
And that's what you want to study. So that became the workhorse of puzzling out all of the science that was associated with the supernova 1987A.
Okay.
And there were some interesting discoveries, just to go down this track a little bit. Prior to the explosion of that supernova, most people thought supernova, the progenitors were these red supergiant stars at the end of their lives. For example, Betelgeuse, which just happened to be also in the constellation Orion. And if someone were to point out, do you know any stars that you can see in the sky with your eye today that may go supernova, maybe tomorrow or maybe 1,000 years from now? Betelgeuse is on that target list. Right? And you can easily see it with the unaided eye.
Easily. It's one of the few stars that you can actually, with your eyes, see the color of the star.
Yeah, and that color being?
Red.
Red. So what we discovered was, and this comes from essentially looking at an image taken of the star field where the supernova went off, looking at it after the supernova brightness declines, and then comparing that photo to one that was taken before the supernova went off, and you actually look for the star that's missing. Obviously, that's the one that blew up. And that star was a blue supergiant. It wasn't a red one.
Right.
So what we figured out is that these stars, these massive stars near the end of their lives, they actually switch back and forth from blue to being red in a relatively short period of time. And so where it actually explodes, of course, we can't predict, but it could either be in the red side or it could be on the blue side or even halfway in between. Right? It's just a random type of thing that's going to happen when it explodes.
And what causes that change is as they start to die, those shells we mentioned where other things are fusing, like there's a shell around it where hydrogen is fusing into helium still, and so forth. But as those heat up, they expand and go red because an expanding gas cools, right? But as that temperature, that outward pressure heat cools off, they'll collapse in, which now it's compressing, and it'll turn back towards blue.
That's right. And to give you an idea of how much energy is typically released in an average supernova, here's one way to think about it. The sun, our own star, will be on the main sequence, happily converting hydrogen into helium for a total lifetime of about 10 billion years. That's with a B, 10 billion years, right?
Right.
10,000 million years for people in the UK, okay? Now, if you take all of the energy that the sun will output in its 10 billion year lifetime, multiply that by 100, and release that in 1 second, that is the energy output of a typical supernova.
This is why most of it glows in the ultraviolet, X-ray, and gamma ray spectrum.
This is why we don't want to be on a planet orbiting one of these stars that goes supernova.
Right.
That is danger. In fact, there are telltale signs. It takes a long, tremendous amount of mass loss at the end of the life of a massive star. There are signatures over many thousands of years that would point to the star being unstable, which hopefully allows you enough time
to get out of the way.
To build, to develop space technology to get the heck out of that star system,
Yes.
so that you don't get, extinguishing type of an event occurring, right, to life forms.
Yep.
Now, the interesting thing about the fact that the supernova 1987A was blue and not red when it actually exploded meant that the star was actually smaller than what it would have been as a red supergiant. So these stars then, when they're at their later stage of their life, these supergiant stars actually increase and decrease in size. They're very very unstable.
Right.
So when the progenitor to 1987A exploded, it was a blue supergiant star. It was actually smaller than if it would have been at its phase where it was a red supergiant. Because it was smaller, it took more energy. It consumed more of the energy in exploding the material to getting it outwards, to reach the escape velocity, to creating the supernova remnant. And because it took more energy, there was less energy that came out in the form of optical light. So the supernova, one of the things that was noticed was it wasn't as bright as what it should have been. And that's because it was a blue supernova being smaller than if it would have been a red supergiant.
Supergiant. Right.
Yeah. So because it was a blue supergiant, it consumed more of the energy than if it would have been a red supergiant, and there was less energy to go around, if you like, to come out in the form of optical light.
Right.
So it wasn't as bright as we would have expected it to have been, given the distance of the Large Magellan Cloud.
I'm trying to think of an analogy for folks, to think of, and all I can think of is when you blow up a balloon, you know how to stretch, and you can actually see through the balloon if you blow it up enough.
Right.
So light can get through it, right? Whereas when you let some of the air out and it gets smaller, it gets opaque again. You can't see through it anymore.
Right.
So the same type of thing is going on. The bit larger, the more puffed out the star is, the more visible light can get through it because its skin is thinner. Whereas when it collapses and gets bluer and is smaller in size, it's thicker and not as much light can get through it.
Yeah, and you can even think of it in terms of escape velocity, right?
Right.
How much easier is it to launch a spacecraft from the International Space Station to head to the moon than launching the same thing from the surface of the Earth, right? It's much less energy required because you're already that much further away and you're in space, right?
Right.
You don't have to worry about plowing through the atmosphere and all of that. And than it is to launch, obviously, a rocket from the surface of the Earth.
I'm laughing because that's something that we get all the time too. Is people think that there's no gravity in space. There's lots of gravity in space.
Well, you just think of it. How does the Earth orbit the sun if there's no gravity in space?
Right. How does the moon orbit the Earth if there's no gravity in space?
How does our sun, along with the planets and everything else in our solar system, orbit the center of the Milky Way if there's no gravity in space? How does the astronauts on the International Space Station, how they maintain their orbit if there's no gravity in space? They would fly in a straight line at a constant speed.
Right.
And I think this all comes, you're kind of barking down this thing that I always hate. The fact that if you see, astronauts in the International Space Station, you see them floating,
they're weightless.
They're weightless. And people would say, look, there's no gravity in space. How else are they weightless? What would cause that? The thing is that they're falling around the Earth in their orbit at the same rate that their space station is falling around. So they don't push on the interior walls in any way.
Right.
That's what's happening, right? And so it would be like, for example, and it gets back to the Galileo's experiment, whether he did it or not, of dropping various objects off the Leaning Tower of Pisa and saying that regardless of their masses, they fell at the same rate. In fact, we did that experiment back on Apollo 15 when they dropped a geological hammer and a falcon feather. And why they picked the falcon feathers because the lunar module nickname was the Falcon.
Okay.
So they dropped the feather and the hammer at the same height above the lunar surface. And when you watch, it's a grainy video, but there's enough detail, enough resolution that you can see that the astronaut let both objects go at the same time and they hit the lunar surface at exactly the same time.
At the big vacuum chamber at, forget the name
Ames,
of that.
I think Ames, yeah.
They repeated this experiment. And
yes, and NASA Glenn, I think, has a big one.
They fall at the same rate, folks.
Yeah, we've tested this over and over and over again. Right?
Another way to look at weightlessness is if you're in an elevator, and hopefully this will never happen to you, but if you're in an elevator and the cables break, you're weightless for a while. Because you're falling at the same rate as the elevator. So if you pushed off from the floor, you'd float where you were in the elevator till it came to a stop. And that's why I hope you never.
Well, you could actually show that to be the case. Imagine you had a very strong friend.
Yeah.
Right? And you probably open the elevator doors, and let's say you're up, 50 stories above the ground. And let's ignore air resistance, right?
Right.
And you probably open the elevator doors, and before you fall down the shaft, you stand on a scale, okay?
Right.
And you look down and you see your weight, not your mass, your weight. Okay? Now attach that same scale, let's say by Velcro, to the bottom of your sneakers, your feet. And let's say you got a little miner's cap on with a light on it, okay? And your friend who's strong lifts you up off the ground, holds you over the elevator shaft, and drops you. And as you fall straight down, remember we're ignoring air friction here, you look down at the scale, what does it read?
0.
So you're weightless.
Right.
Why? Because you and the scale are falling at the same rate. You're not pushing in on the scale, right? So that's what's happening there. And that's why the astronauts are floating around the International Space Station, because them and everything in their space station is falling around at the same rate.
Yes.
Exactly. And people get this notion, because we even use it, whether you're reporting on it or not on different stories, that they're in this zero-G, zero-gravity environment, and that is not true. The station would not orbit the Earth if there was no gravity. It's traveling at a certain speed, so it would fly off in a straight line at a constant speed, unless some external forces, of course, operate on that vehicle.
And believe we're out of time.
I think we're out of time already. So
Yes.
I just want to say before we leave that our next podcast will be a week from now. That will be on April the 18th at 3 p.m. Central Daylight Time. We are in the daylight time, of course, not standard time.
Right.
And the other thing is, if you're interested in physics, if you want to learn more about astronomy or astrophysics or science in general, please consider coming to the University of North Dakota. Please consider enrolling in one of our STEM programs, including physics and astrophysics here in our own department. And as always, we have a quote.
Okay.
And fittingly, since we mentioned the Challenger, that it exploded in January of 1986, this quote actually comes from one of the astronauts that was on board that vehicle. And this is from Krista McAuliffe, who was going to be the first teacher in space at the time.
Yep.
And her quote we're going to say today is, "I touch the future. I teach." Thank you very much for
Thank
watching.
you, folks. Y'all have a great week.